All right, example 3. So what if we've got a block of mass 20 kilograms, and once again, sliding on a frictionless table, no air resistance, nothing like that. So it's just about the energy being put into it with VI equals 4 meters per second. So it starts off with a velocity of 4 meters per second, and then acted upon by a force of 35 newtons at an angle of 20 degrees above the horizontal for a distance of 15 meters. What's its speed afterwards? Well, we don't have to worry about the force of friction, so we don't have to worry about the normal force, so we don't have to break down that force of 35 newtons into its components. We just have to figure out how much work does it put into our system. So the work is going to be force times distance times cosine theta. So force, magnitude, times displacement magnitude, times cosine theta. What's the force? The force is 35 newtons. What's the distance that it travels? 15 meters times cosine of 20 degrees. We plug that into a calculator, and we get that it's 493.3 joules. All right, conservation of energy formula. We know that the energy at the beginning in our system plus the work put in is equal to the energy at the end in our system. So what's the energy in the beginning? Remember, it didn't start at rest this time. This time, it had an initial velocity of 4 meters per second. So we have to include that. 1/2 mvi squared plus what work do we put in? We put work into the system. We continue to accelerate it. So the environment acted upon the object, not the object losing energy to the environment. So if that's the case, that means 1/2 mvi squared plus work. How much work? 493.3 joules is equal to the energy at the end, 1/2 m velocity final squared. And I'm cheating a little bit. These should really be magnitudes, actually, because we're talking about the speed. All right, so here we just plug things in. So 1/2 mvi squared plus 493.3. What's the mass? 1/2 20 is the mass, 20 kilograms, times its initial speed, 4 squared, plus 493.3. We plug that into a calculator, and we get that that's 653.3 joules. So that means our energy at the end, which is equal to just the motion in the velocity, just the energy in the velocity, energy kinetic, is going to be 1/2 mvf squared, which is equal to energy at the beginning plus the work put into the system, or 653.3 joules. So we solve this with algebra. We get that Vf is equal, speed, sorry, not velocity. Vf is equal to 2 times 653.3 divided by the mass, which is 20 kilograms, and then we also have to take the square root of everything. We plug that into a calculator, and we get that it's 8.08 meters per second. There we go. We know what the starting energy is. We know how much work goes into the system. We put those things together. That gives us the ending energy. And then we figure out what energies are going to be being used at the end. It's just the kinetic energy. That's the only energy that's going to be in our system at this point. So we know that the total ending energy is equal to the kinetic energy at the end. And we just solve for it.